Now that we know what a parametric function is and how to graph it, we're going to start looking at how to find the slope of a smooth curve defined by a parametric function at a point xy. So the slope, or the change in y with respect to x, is the change in y divided by the change of x. That's our function of slope. And so if I want to find the change in y with respect to x, I need to find the change in y with respect to time divided by the change of x with respect to time. So that's just delta y over delta x. To find the second derivative, we take the derivative with respect to x of our dy dx. So using implicit differentiation, that is the same as the derivative with respect to t of dy dx times the derivative of t with respect to x. We can change multiplication into division by flipping the fraction and end up dividing by dx dt. So let's look at our very first example. So in this example, we're asked to find dy dx at time 1 and the second derivative at time 1. So we're going to start by looking at our x function, which is defined by 2 the square root of x. And let's differentiate this with respect to time. And we find the derivative of x with respect to time is equal to 1 divided by the square root of t. Next, we'll do the same thing with y. So we're going to find the derivative of y with respect to time, which is equal to 6t minus 2. Now that we have the two components, we're ready to find the derivative of y with respect to x, which is simply the derivative of y with respect to time divided by the derivative of x with respect to time. So that would mean that we take 6t minus 2 as our numerator and 1 divided by the square root of t as our denominator. Simplifying this fraction down, we'll end up with square root of t times 6t minus 2. So we were asked to evaluate the first derivative at t equals 1. So we simply use substitution, replacing every t with 1 to end up with 4. Next, we were asked to find the second derivative of y with respect to x evaluated at t equals 1. So that's just our first derivative divided by dx dt. So our first derivative, I'll need to use the product rule to figure this out. And then I'll just copy down my dx dt and simplifying down the expression. We end up with 9t minus 1. Then evaluating the second derivative at 1, we get an answer of 8. Next example, we're asked to find the equation of the tangent line to our parametric curve. So first thing we have to do is find the point x, y. So plugging in 3 pi over 4 in place of t and x, we'll simplify this down. We get x is equal to negative 2 to the square root of 2. Do the same thing for y. And I find y is equal to 3 to the square root of 2 over 2. Now that I have a point, the next thing I need to do is find the slope. Now, the slope is found by taking the derivative of y with respect to x. So that means I need to differentiate my y with respect to t, and then differentiate my x with respect to t, and divide the two. And evaluating at 3 pi over 4, we find the slope of the tangent line to be simply 3/4. Now that I have a point and a slope, I'm going to use my point slope form of the line to find our equation of the tangent line. Plug in the point y, the slope, and the x of the point, and solving that for y, I get my equation of my tangent line. Next, we're going to look at how to find the parametric arc length. So let's say we have a parametric curve in the following shape. And let's say I wanted to find the distance from A to B of this parametric curve. And I'd say the arc length is equal to, in terms of position motion problems, the total distance traveled. So the total distance I travel along that curve, starting at A to B, is equal to our arc length. So if we're asked to find total distance, Now we're going of a parametric curve, we're going to use the formula highlighted above. So let's look at this example here. We're asked to find the arc length of the curve. So I'm going to start by finding my derivative of x with respect to t, my derivative of y with respect to t. Then I'm going to take my formula from my integral from 0 to 1 of the square root of dx dt squared plus dy dt squared. And then we're just going to simplify this down. I notice I have a GCF underneath the square root, so let's factor out that GCF. Then I can break up my square root and take the square root of the GCF, which is just 2t, times by the square root of 1 plus 36t squared. And then I'm going to use u substitution in order to solve this integral. I'm going to let u equal the thing underneath the square root. Then I take the derivative of u and solve for dt. And then I'm going to substitute into my original evaluation problem u in place of that 1 plus 36 t squared, and in place of dt, du. Simplifying down, end up with a constant of 1 over 36 times by u to the 1/2 du. Now this is an integral that we can easily evaluate, so I'm going to evaluate this integral. Then replace my u with what I found it equal to with the 1 plus 36t squared. And then we're going to find our integral from 0 to 1 of this new statement. Substituting in 1 and then substituting in 0 and simplifying down. And we get our arc length is equal to 1 over 54, 37 to the 3/2 minus 1. So that's the total distance traveled by this particle starting from time 0 to time 1.
Discussed earlier, arc length leads it very closely to particle motion problems as the total distance traveled. In fact, parametric equations are very useful in other particle motion problems that are moving in two directions, vertically and horizontally. So let's look at our particle motion first. Our derivative of the x with respect to t is our horizontal direction of our particle. So it's the particle's velocity of the particle in horizontal direction. Whereas the derivative of y with respect to t is the velocity of the particle's vertical direction. So x is moving horizontally, y is moving vertically. Our position equation can also be written as a vector. And when we put it in a vector, we just put it in a chevron. So we just list our x expression in terms of t, comma, our y expression in terms of t. And that gives us our position vector enclosed by chevrons. And then if we want to figure out our velocity vector at time t, we simply take the derivative of the position function with respect of the x with respect to t minus the derivative of the position function of y with respect to t. And we do the same thing with acceleration. It's just the second derivative. So it's the derivative of the velocity function or the second derivative of the position function. So nothing's changed, just the way that we note it is now in vector form as compared to what we did previously. The rate of change of y with respect to x, the slope of the tangent line of the curve, and the slope of the position vector is all figured out by doing dy dx, what we've been doing, but we just have to do it in parts here. And then our second derivative is equal to the rate of change of the slope of the curve with respect to the x. Our speed of our particle, absolute value of velocity, can also be noted in two different ways. We can sometimes call it its magnitude, and we put it, instead of just absolute value, we'll put it in 2 bars. That means the magnitude of the velocity vector, or sometimes called the norm of the velocity vector, is all equal to the length of the norm of the velocity vector. And so that's going to be that square root of the derivative of x with respect to t squared plus the derivative of y with respect to t squared, which looks very familiar to our arc length, except we're not doing the integral. So that's the difference between that and the arc length function to get the length of the normal curve. Another formula that you need to know is the length of the arc from time A to time B is that norm that we just talked about formula evaluated from A to B. And this is also the same thing as the distance traveled of the particle from A to B. And remember that the integral from A to B of the absolute speed function is equal to the total distance traveled along a straight line of a curve. And so it translates just the same in terms of vectors and parametric functions. All right, let's look at our first particle motion problem involving parametric equations. So first, let's rewrite this as a vector for our position vector. And we're just simply going to rewrite it in chevrons. So we have our position vector is t cubed plus 4t squared, comma, t to the fourth minus t cubed. And then in part A, we're asked to find the velocity vector at t equals 1. So we know that the derivative of position vector is equal to velocity. So we're just going to differentiate each of these individually and then evaluate with t is equal to 1. And we end up with our velocity vector at 1 is 11, 1. Although I don't know the exact path of this particle, what this velocity vector at t equals 1 tells us is whatever the path of the particle is at that moment t equals 1, most of the energy is being transferred to the right, since it's moving to the right 11 times faster than it is moving up. But it is not traveling horizontally or vertically, it's traveling along a curve. So make sure that when you're looking at this, the x factor of our vector of the velocity tells us our left and right movement. The right tells us our up and down movement along the curve. Moving on to part B, we're asked to find the speed of the particle at t equals 1. So we already have the velocity of the particle at t equals 1, and we know speed is just the absolute value of the velocity, which is also found by the square root equation written here. So I just take this as the speed is equal to, at 1 is equal to the square root of 11 squared plus 1 squared, which is simply the square root of 122. Now, usually you'll have some sort of units. Just remember velocity and speed is units over time. Finally, in part C, we're going to find the acceleration vector at t equals 1. So we're going to recall our velocity vector from part A. And we know acceleration is simply the derivative of velocity. So we're going to differentiate each side individually. So differentiate the x side and then the y side. And that is our velocity vector. And then we're to simply replace every t with 1 to find out the acceleration at time 1, which is simply 14.6. In our last example, we're also going to look at particle motion, but this time our particle motion is not going to be translated into a vector. So we're going to keep it as parametric equations. So you can either use parametric equations translated into vectors or not. So in part A, we're asked to find the derivative of y with respect to x. So remember, we just have to differentiate our y with respect to time. In this case, we get negative 2 cosine of t, and then differentiate the x with respect to time, and we get 4 sine of t. And then we just take our derivative of y divided by our derivative of x and simplify down. Now, it's very useful to always simplify, especially these trigonometric functions when you have quotients here, because I'm going to have to find the second derivative in a moment, and it's easier if I can differentiate this expression than having to use the quotient rule in our work. So to the second derivative, we take the derivative of our last answer, and we know that cosine of t's derivative is negative cosecant squared, so that becomes a positive 1/2 cosecant squared of t. And then I always divide by the derivative of x with respect to time, so 4 sine. Simplifying this down, we get 1/8 cosecant cubed of t. And that's it for example A. Part B, we're asked to find the path of the particle as it intersects the x-axis twice. So let's see what this means. I don't know exactly what this particle looks like, but I know it's some sort of curved shape. So let's say it looks something like this. And I need to know I want to know the distance traveled of the particle in between those two x-intercepts. So first thing I need to do is I need to figure out what my x-intercepts are, and then I'm going to figure out my total distance traveled using our formulas that we've learned before. So how do you find when the x-intercepts of a graph? Where our x-intercepts are when our y is equal to 0. So first thing I'm going to do is take my y equation from the very beginning, which is y is equal to 1 minus 2 sine of t, and set it equal to 0. Solving this function, we end up with sine of t is equal to 1/2. So I got to go back to my unit circle from 0 to 2 pi. When is sine of t equals to 1/2? Well, the first time that happens is in quadrant 1 at pi over 6. And the second time our y is positive is in quadrant 2. So that's going to be 5 pi over 6. So those are my 2 points. Now I need to find my equation for total distance traveled. So I recall that's the same as arc length. So this is the equation I will be using. And I'm going to replace my a with pi over 6, my b with 5 pi over 6. And I'm going to use the derivatives we found in part A to replace up here. And I'm going to square each of those derivatives. And since it only asked us to find it but do not evaluate it, I can stop here.